Okay, so let's look at isotopes. They are versions of the same element that have different numbers of neutrons. So here's calcium. You can see it has a decimal number here. That means it has several different isotopes, and the average or the mean of that gives us this decimal number. So let's just recap. What is an isotope? So an isotope are atoms of the same element with the same number of protons, the positive particles, but a different number of neutrons. That means they have different mass number. So the atomic numbers, the amount of protons, it is going to be the same. And the electrons is equal to the protons, it will also be the same. Here we can see calcium. The protons are all the same, but the neutrons, the mass number differs. I'm just going to leave it here so that you can quickly check it again. Protons are the same, but the mass number differs. They're all calcium's isotopes. So what is the relative atomic mass? So the relative atomic mass is a weighted average of all the isotopes of an element based on their abundance. How much there is of that specific isotope. So here they are like weighed, and then the average or the mean is taken. So you can see most calcium atoms are like calcium 40, that's about 96.9%, but small amounts of the other isotopes exist too. So that is why on the periodic table, it is not a whole number, but it is a decimal number. So it's not exactly 40. Yeah. So when we look at the table, which isotope has the greatest abundance? Like which one would be more? If you look here at this table, which one would be more? Which one of these isotopes would you get the most in nature? If you said 96, calcium 40, you would be correct because that is the most that is found of that specific isotope. Look at this one, these two. They're so little. This one is of greater abundance. We get it more. It is occurring more in nature. So the relative atomic mass, AR, of an element is the mean, the average mass of atoms. So we always compare it to 1/12 of the mass of carbon atom. So carbon 12 atom, just a little bit of terminology for you there so that you can remember that. Now we are going to calculate. Usually give you a table like this. There is two different chlorine isotopes that we are going to now work out, and we can use this formula. Just get my pen. Okay, so here's the formula. Relative atomic mass, AR, is calculated using the following equation. That means the sum. And the isotope abundance that we are going to divide it by will always be 100, because this together must give us 100 in percentage. Okay, so let me quickly just erase again. Okay, so sum. Okay, let me get my pencil again. So we're going to work out the relative atomic mass of each isotope times the percentage. Okay, so it's going to be 35 times 75. So let's start here at the top. 35 times 75. Oopsie, why is my 5 looking so weird? Is it 37 times 25 plus divide by 100. My writing is not as neat. So we can put that in your calculator. Then let's say we would get 35 times 75 would give us 2, 6. Get my cable. 2, 5 plus 37 times 25 will give us 925. Remember, divide by 100. And that would give, oopsie. That would give us, let me write it here. Would give me 35,5. Okay, so relative atomic mass of chlorine. Oh, I'm going to the next page. Of chlorine is 35. I'm getting close. There, yay! Okay, so now I have a little bit more space. So let's calculate the relative atomic mass for copper to 1 decimal point. Okay, so here is our copper in the table. Remember, this means the sum, and the isotope abundance is always going to be equal to like 100 because we're working with percentages. Okay, relative atomic mass of each isotope. So it's going to be, let's do this one first. Copper 63 times the percentage 69,2. That percentage. And remember sum, so we're going to add 65 times 30,9. Okay, let's put them all together, divided by 100. You can put that into your calculator. 2 plus 65 times 38 divided by 100. That gives us 63,616, but we only want it to 1 decimal point, so only to that one. If we round it off, that is not bigger than a 5, so it's going to stay 6. Yay! Maybe I should have put confetti. Let's work out the relative atomic mass of gallium. Again to 1 decimal point, so we are going to substitute it again into our equation. Remember the sum, and to 100 divided by 100. Okay, so we take the one isotope, 69 times, which one is more in abundance here? Which gallium isotope? It is this one, gallium 69. It's in abundance. Plus, because we're working with the sum, okay, 71 times 39,9. Put that in brackets. That one is a little bit unneat. divided by 100, and that will give us 69.8. Yay! So here we have our answer. Just want to check ourselves. Now here is another question. Many isotopes are radioactive and can be used in the industry. The stable isotopes of titanium are these ones. Titanium 46, 47, 48, 49. We need to calculate the abundance of titanium 50. So how would we do that? We know that these percentages together with titanium 50 should give us 100. Okay, so let's go and add them together. So first step one is we are going to add them together. Let's see, it needs to give us 100. 80, oh no, 8 plus 7.3 plus 73.8 plus 50, no, 5.5. Now let me erase that one. Let's make it better. Let me write it more neatly. Okay, so first step one, we're going to add the percentages. You try to make it like this, sum of the percentages. Okay, so adding it, then it together would give us 94.6%. Okay, so if we take the 100 and we subtract it, we would get the abundance of titanium. Oh, let me write it again. It's a bit unneat. Titanium 50. We're going to take the 100% minus 94.6 to get the abundance of titanium 15. That will give us 5.4% would be the abundance for titanium 50. Let me just put that away. Then also if we look here at our little pie chart, then we can see those ones added together. Oopsie. Those ones added together. Yeah. So remember, the relative atomic mass is like an average or the mean, but it's weighted based on how common each isotope is. Here's another little question. What do you think is the answer? So lithium 6 reacts vigorously with water. What would happen with lithium 7 when it is placed in water? Do you think A, no reaction would take place with lithium 7, oh my goodness, and water? B, lithium 7 would be more reactive than lithium 6? Or C, lithium 7 would react the same way as lithium 6? Did I say 7 would react the same way as lithium 6? Oh my goodness. Please put your answer in the comments. Here's another little question. What do you think is the answer? So lithium 6 reacts vigorously with water. What would happen with lithium 7 when it is placed in water? Do you think A? So please like, comment, what are you struggling with? What video do you want to see next, or what question or equation do you want to see next? And then I also put like a little freebie in the chat. It's kind of like a planner if you want to get a little bit more organized for your exams. And then there is also different types of freebies if you want to check them out. Link would be in the comments. Have a nice day.